Welcome to Advanced Module 02 on Data Center MVAC systems. In this session, we'll focus on how to convert standards and owner requirements into traceable design, test, and operating evidence. We'll cover key components like owner requirements, basis of design, standards matrix, design response, test evidence, and operational control. This module is designed to ensure that every aspect of the system is aligned with the necessary standards and fully documented for accountability and performance. This traceability is crucial for maintaining system integrity and compliance throughout the lifecycle of the data center. In this module, we focus on standards, governance, and certification for data center MVAC systems. Our goal is to convert standards and owner requirements into traceable design, test, and operating evidence that ensures everything is aligned and verifiable. We'll connect the design intent with physical behavior and controls using practical engineering examples tailored for client training. By the end, you'll be able to explain the entire process from load to rejection, calculate governing duty and operating margins, review different operational states, and build an auditable test and handover pack. This content is designed for owners, operators, engineers, commissioning authorities, and vendor teams who all play a role in maintaining system integrity and performance. In this module, we focus on evaluating the data center MVAC system through a risk lens and decision hierarchy. We look at 5 critical factors together: safety, thermal continuity, maintainability, efficiency, and evidence. Starting with safety, the goal is to protect both personnel and equipment by staying within the approved operating envelope and relying on local safeties as the final authority. Next is continuity, which involves governing the approved system topology, clearly documenting maintenance limitations, protecting assumptions about independence, and requiring approval for any deviations. Then, maintainability ensures we can isolate a single asset without disrupting essential duties, provide adequate access for servicing, and verify that systems can return to service efficiently. All these factors work together to ensure the MVAC system operates reliably and safely while meeting key project requirements and design bases. This module focuses on standards, governance, and certification for data center MVAC systems. We'll explore a repeatable engineering process that starts with the design intent and carries through to operation. The key steps include defining the design intent, gathering inputs, performing calculations, developing the architecture, implementing controls, conducting testing, and gathering evidence to operate effectively. An important part of this process is clearly defining the protected load and envelope while declaring assumptions and potential failure states. The architecture phase involves adopting the latest code additions, including ASHRAE 90.4 to 2025, OSHRI TC 9.9 classes, ISO/IC 30134 KPIs, certification commitments, and local authority requirements. For controls, we focus on crucial performance metrics such as power usage effectiveness, or PUE, which compares facility energy to IT energy, water usage effectiveness, or WUE, and cooling energy intensity. These metrics help us monitor and optimize the system's efficiency throughout its lifecycle. In this module, we'll focus on standards, governance, and certification for data center MVAC systems. By the end, you'll be able to design, test, and operate these systems effectively. We'll cover key competencies including design, where you'll learn to define system boundaries, set performance criteria, select capacity and redundancy philosophies, and review maintainability. On the calculation side, you'll gain skills to calculate governing duty, ensure unit consistency and margins, and state your assumptions clearly. Control competence will also be addressed, ensuring you can manage system operations accurately. Additionally, we'll explore evidence competence, focusing on owner requirements, the basis of design, and how standards apply. Important concepts like the standards matrix and design response will connect these ideas, preparing you to meet owner project requirements and optimize efficiency measures like PUE and WUE. In this module, we'll dive deep into standards, governance, and certification specifically for data center MVAC systems. Our agenda takes a practical approach, guiding you step by step from the initial design basis all the way through to field evidence. We start by defining the system and its boundaries, focusing on how to convert standards and owner requirements into clear, traceable design, test, and operating evidence. This includes understanding owner requirements, establishing the basis of design, developing a standards matrix, creating design responses, and gathering test evidence. Next, we'll cover sizing and selection, emphasizing the importance of adopting the right code additions such as ASHRAE 90.4 to 2025, OSHRI TC 9.9 classes, ISO/AC 30134 KPIs, certification commitments, and local authority requirements. Controls and alarms are critical, so we'll discuss freezing applicable additions, mapping each clause to a design response, assigning evidence ownership, verifying installation evidence, closing test and defect records, and transferring controls to operations. Finally, commissioning and operations involve thorough audits and reviews. This includes a clause-to-design audit, drawing-to-field walkdowns, point-to-point evidence checks, meter boundary verification, certification mock audits, and an operations readiness review. Throughout, keep in mind key terms like OPR for owner project requirements, BOD for basis of design, and metrics like PUE and WUE that help measure efficiency. This detailed, workstream approach ensures that every step is documented and compliant, setting a strong foundation for successful certification. This slide focuses on governance and standards for data center MVAC systems, emphasizing one governance stack with different authorities. It starts with jurisdiction and contract obligations, then layers in standards and certification schemes to guide design, testing, and operation. At the top, we have mandatory requirements like adopted laws, permits, and statutory safety and environmental codes. Next, consensus-based and sector standards such as ASHRAE, TIA, IEC, ASME, and performance certifications from AHRI and CTI provide technical frameworks. Owner-specific requirements, including service-level agreements and sustainability certifications like LEED or Green Mark, add another layer of control. These governing requirements flow down through design, submission, installation, testing, and finally into ongoing operating control, ensuring compliance at every stage. Key components like chillers, pumps, cooling towers, CRAC units, and sensors are all covered by this structure. Importantly, voluntary standards or owner waivers cannot override adopted laws or authority having jurisdiction conditions. Any conflicts must be resolved within the authorized governance process. This ensures a clear, enforceable framework for maintaining safety, performance, and reliability. On this slide, we're focusing on the concept of system boundary and interface ownership within a data center MVAC system. It's essential to understand that every interface in the system must have a clearly defined owner, along with specific signals, acceptance criteria, and restoration rules. This ensures accountability and smooth operation across various domains. Starting with the heat or fluid source interface, the owner is responsible for requirements, basis of design, standards compliance, design response, and test evidence. For the mechanical boundary, key factors include supply and return conditions, pressure class, as well as drain, fill, and vent points. Moving to the controls boundary, the local controller manages safety functions, while the central platform operating system, or building management system, coordinates approved modes. Manual overrides are also controlled and alarmed here, ensuring no unsafe actions occur unnoticed. The electrical interface involves managing normal, standby, and emergency power sources, including sequencing for load shedding and restart, alongside metering boundaries to track consumption accurately. Each of these interfaces, heat or fluid, mechanical, controls, and electrical, must be managed with clear ownership and well-defined parameters to maintain system integrity and reliability. This thorough approach supports compliance with standards and effective governance throughout the system lifecycle. In this module, we focus on standards, governance, and certification within data center MVAC systems. We'll take a real-world look at equipment visualization to help you identify key field assets, service clearances, and potential failure domains. It's crucial to understand owner requirements and the basis of design, which guide the standards matrix, design response, and test evidence, ultimately shaping operations control. When inspecting equipment, pay close attention to nameplate duty and approved submittals, as well as access points, isolation protocols, drainage, lifting capabilities, sensors, actuators, and local safety features. Operationally, it's important to monitor the lead and lag states, set points and modes, and critical parameters like flow, temperature, pressure, and power. Keeping these elements in mind ensures compliance and optimal performance throughout the lifecycle of the system. In this module, we're focusing on the critical elements of standards, governance, and certification for data center MVAC systems. A credible calculation starts with a controlled input register, ensuring all design criteria and declared assumptions are clearly defined. Key factors include understanding the load and duty requirements, based on adopted code additions such as ASHRE 90.4 to 2025 and OSHRE TC 9.9 classes. We also consider climate and environmental aspects, aligning with ISO/IEC 30134 KPIs, certification commitments, and local authority regulations. Temperature architecture plays a vital role, covering supply and return values, dew point margins, and minimum and maximum allowable conditions. Hydraulic and airside criteria must be carefully specified, along with plans for system redundancy and future growth. Throughout, we refer to essential concepts like the owner project requirements, basis of design, as well as key efficiency metrics such as PUE and WUE. This comprehensive approach ensures the system is designed to perform reliably, efficiently, and in compliance with all necessary standards. This slide focuses on the requirements to evidence digital thread, which is a crucial part of managing standards, governance, and certification in a data center MVAC system. Each obligation starts with an owner and includes a design response, a verification method, an acceptance rule, and a retained evidence record. The process begins with identifying the source, such as a law, authority having jurisdiction, or a standard owner. Each requirement is assigned a unique ID that precisely defines the obligation. Next, the design phase captures the basis of design, system operation, drawings, or schedules. Approved submittals like model performance data are reviewed before installation, where equipment tags, locations, and configurations are documented. Verification involves calibrated inspections and tests to ensure compliance. Acceptance is then documented with pass or fail decisions, or exceptions if applicable. Finally, ongoing operation uses standard operating procedures, trend monitoring, management of change, and retention of records. The slide also highlights examples of generic trace IDs tied to different aspects, such as cooling path maintenance, topology and control documentation, witness testing, and evidence records. The closure gate ensures the correct addition, approved design response, installation verification, calibrated evidence acceptance, and handling of deviations. Remember, a certificate or dashboard alone does not replace the need for traceable, underlying evidence that documents compliance comprehensively. This thorough traceability is essential for meeting governance and certification requirements effectively. In this module, we're focusing on the critical aspects of standards, governance, and certification for data center MVAC systems. One key point is to freeze all sizing inputs before selecting equipment, which ensures accuracy and prevents costly errors later. It's also important to separate design margin from redundancy to clearly understand your system's reliability. We consider several essential inputs like adopted code additions, including ASHRE 90.4 to 2025, OSHRE TC 9.9 classes, ISO/IEC 30134 KPIs, and certification commitments, along with any local authority requirements. Boundary conditions play a major role too, from normal operation to worst design climate or load scenarios, concurrent maintenance conditions, and handling single failures. Selection checks and field verification ensure that the equipment chosen meets these stringent requirements and performs as expected. Remember, aligning with the owner project requirements and basis of design, while monitoring metrics such as PUE and WUE guarantees your data center's efficiency and compliance. This module covers key standards, governance, and certification metrics critical for data center MVAC systems. First, we look at power usage effectiveness, or PUE, which is calculated by dividing the facility's total energy by the IT equipment energy. For example, a facility using 14.4 gigawatt-hours total with 10.8 used by IT yields a PUE of 1.33, showing energy efficiency. Next is site water usage effectiveness, WUE, which measures water volume used per unit of IT energy consumption. Here, 18,000 cubic meters of water corresponds to 1.67 liters per kilowatt-hour, helping track water efficiency. Requirement closure tracks progress by dividing verified closed items by applicable ones, counting only accepted closures and excluding approved non-applicable items. Evidence completeness gauges readiness by comparing verified evidence sets to required sets, but does not imply compliance on its own. Qualitative risk scoring uses a matrix of likelihood times consequence to assign risk bands, emphasizing clear definitions without presenting results as exact probabilities. Finally, residual risk reassesses the likelihood and consequence after controls are verified, requiring clear authority, review dates, and operating limits. A crucial boundary rule is to never compare sites or periods unless energy sources, IT meter locations, water scopes, intervals, and data quality treatments are fully aligned, ensuring fair, meaningful analysis. When we talk about PUE and WUE, it's crucial to first define the boundary before interpreting the numbers, because the meaning of these metrics depends heavily on meter placement and reporting scope. Starting with PUE, or power usage effectiveness, this metric is calculated by dividing the total energy consumed by the entire facility by the energy used specifically for IT equipment. This includes all energy within the declared facility boundary, such as cooling, power losses, lighting, and support loads. An example calculation shows 14.4 gigawatt-hours divided by 10.8 gigawatt-hours gives a PUE of 1.33, indicating the relative efficiency of the power use. Similarly, WUE, or water usage effectiveness, focuses on water usage within a defined boundary called the site water boundary. The water use is measured in liters and divided by the IT energy consumption in kilowatt-hours. For example, 18,000 cubic meters converted to liters divided by 10.8 million kilowatt-hours results in 1.67 liters per kilowatt-hour. It's important to declare all water uses included, like cooling makeup and blowdown. To make fair comparisons using these metrics, we need to ensure the same source energy conventions, consistent IT meter locations, equivalent water scopes, matching time intervals, and validated meter quality, along with normalized operating contexts. This consistency acts as our comparison gate to accurately assess and compare data center efficiency. Here we have a worked example focusing on operating margin and equipment decisions in the context of standards, governance, and certification. The process starts with the given inputs, which then lead to a calculated result. The key here is to link these numbers to factors such as capacity, controls, maintainability, and failure response, ensuring a comprehensive understanding of the engineering implications. We begin with the operating margin represented here by a water usage effectiveness, or WUE, of 1.67 liters per kilowatt-hour. This is an important metric as it quantifies water efficiency relative to energy use. Following that, redundancy is checked to govern the approved system topology, document any maintenance limitations, and protect the assumptions of independence between components. Field verification, or remote checks, validate these findings through real-world measurements and inspections. The evidence package includes calculation sheets, approved equipment data, measured results, and signed restoration documentation, all critical for compliance and quality assurance. Finally, the decision phase ties everything together, using the gathered data and verification to guide project choices. Remember, while this training example declares assumptions, final decisions must be based on approved project and vendor data. This structured approach ensures that engineering decisions are robust, traceable, and aligned with project requirements. This module focuses on standards, governance, and certification specifically for data center MVAC systems. We'll be covering the essential control sequence of start, stage, fail, and restore. The process is broken down into several key steps, starting with freezing applicable additions to ensure we work with the right standards. Next, we'll map each clause to a design response to align requirements with practical implementation. Then, it's important to assign evidence owners to maintain accountability and traceability throughout the project. Throughout this training, keep in mind crucial concepts like owner project requirements, basis of design, power usage effectiveness, and water usage effectiveness, as they form the backbone of effective MVAC system governance. On this slide, we focus on the process of managing deviations, risk acceptance, and changes within a data center MVAC system. A deviation is only controlled when four key elements are clear: the governing obligation, the consequence, compensating controls, and a defined closure path. The process starts by identifying the exact source and gap of the deviation. Next, we screen it against safety standards, authority having jurisdiction requirements, and service-level agreements. Then, we analyze the root cause and failure domain to understand the context. Controls are put in place as compensating measures, which must then be verified through testing to ensure effectiveness. Only after thorough verification can a named authority accept the deviation, with defined limits. Finally, the issue is closed by implementing a permanent correction, accompanied by proof and documentation updates. We also have specific risk acceptance gates to consider. Some risks are non-waivable, meaning legal obligations and permits must always be met, and formal authority sought when relief is possible. Residual risk requires ongoing reassessment and clear documentation, including operating limits and escalation triggers. Controls only count once installed, tested, and supported by evidence. Restoration means closing the deviation only after all corrections and retesting are complete and normal system operation is restored. Lastly, we use a qualitative 5x5 risk screening matrix to assess consequences against likelihood, helping prioritize risks in this structured manner. This holistic approach ensures safety and compliance throughout the management of deviations. This slide covers the essential stages for ensuring that a data center MVAC system is acceptable through verified evidence. First, the basis is established by governing requirements like BOD, PNID, and SLO documents. Then, the asset itself must be clearly identified with tags, models, and assigned duties including valves, sensors, and power components. Next, inspection focuses on access, isolation, flow direction, and wiring to make sure everything is properly arranged. Testing involves using calibrated instruments under controlled scenarios to validate performance. Proving the system requires time-aligned trend analysis, looking for pass, fail, and exceptions to ensure reliability. Finally, control involves formal handover, standard operating procedures, management of change, and record retention. The key field rule here is to verify the approved asset and all accessories together as a fully integrated operating system, not just as separate components. This holistic approach is critical for maintaining system integrity and operational success. On this slide, we're focusing on governance registers and the management of change log, which are critical for maintaining control and accountability throughout the data center MVAC system lifecycle. A register is only useful when it clearly defines several essential elements: the accountable owner who is responsible for it, the update trigger that specifies when the register needs to be revised, the minimum required fields to capture key information, and closure evidence to confirm issues or changes are addressed. We break down controlled registers into specific categories like standards, requirements, assets, calibration, test evidence, and deviations or management of change. Each category has tailored minimum fields, such as addition, applicability, or clauses for standards, source and obligations for requirements, and tag, approval, and location for assets. These fields ensure traceability and completeness. Moreover, the digital thread check is an important step to verify that one requirement ID links consistently to all related documents and records, from approved design responses and exact assets to as-used instruments, test records, deviation decisions, and the current operating baseline. This ensures a seamless, auditable trail that supports compliance and effective management of changes in the system. This slide covers the critical aspects of standards, governance, and certification for data center MVAC systems. First, performance, energy, water, and governance metrics are fundamental to making informed decisions. However, these metrics only truly support decisions when 5 key elements are clearly declared: the boundary, interval, data quality, normalization process, and the responsible owner. For example, the metric PUE, or power usage effectiveness, is calculated as the total facility energy divided by the IT energy, with careful alignment of energy boundary and interval. Similarly, site WUE, or water usage effectiveness, measures water volume used per unit of IT energy, where all included water uses must be declared. Thermal compliance is tracked by the ratio of compliant sample time to total time, relying on approved building envelopes and sensor quality. Available cooling capacity is defined as the permitted cooling duty minus the governing load, with any maintenance or failure states explicitly declared. Requirement closure is another crucial metric, measuring verified closed requirements over those applicable, but only accepted closures count. Evidence completeness reflects verified data sets compared to those required, serving as readiness indicators rather than compliance alone. Open deviations are tracked by risk band and age, with clear visibility into ownership, expiry, and escalation. Test and calibration currency is maintained by ensuring valid records match required ones, with all instruments traceable. The governance process follows 5 steps. Define the boundary, source, and interval, validate meters, sensors, and data completeness, normalize for load, weather, and operating state, act by assigning ownership, thresholds, and due dates, and finally, prove compliance through retesting, acceptance, and record retention. A key dashboard rule to remember is that a green metric does not close an unverified requirement, expired test, or unapproved deviation, ensuring integrity in the certification process. Here we have the Clause to Evidence Compliance Matrix, which is a crucial tool in managing standards, governance, and certification for the Data Center MVAC system. The matrix helps us track each requirement from its source, through design response, verification, and finally to acceptance evidence, ensuring nothing is overlooked. Notice that each requirement is identified generically in training modules, but for live projects, it's essential to preserve the exact source, edition, clause, and approved evidence location. This maintains clarity and accountability throughout the process. The matrix is divided into sections like safety, owner requirements, energy, environment, certification, and operations. For example, safety requirements might involve coordinating safety interlocks and access, which are verified by inspections and functional tests, with records duly accepted. Energy requirements focus on defining and validating meter boundaries and efficiency methods, ensuring accurate data collection. A key point to remember is the closure rule. We only close a clause when the governing source is accurate, the approved response is installed, verification is successful, evidence is properly indexed, and all exceptions have been authorized. This rule guarantees that every compliance item is thoroughly addressed before it's considered complete. Overall, this matrix is an indispensable part of ensuring that our project meets all necessary standards and performs reliably throughout its life cycle. In this module, we're focusing on commissioning levels 1 through 3, which are critical steps to ensure the Data Center MVAC system is properly designed, built, and installed before we move on to functional performance testing. At Commissioning Level 1, or CXL1, we conduct a thorough design review and factory acceptance testing. This includes reviewing approved submittals, verifying factory performance and controls, observing key witness points, and ensuring any defects are closed out. Moving to Commissioning Level 2, or CXL2, the emphasis shifts to installation. Here, we verify tags and equipment orientation, check isolation, drains, and access points, inspect cable and pipe terminations, and confirm sensor locations are correct. Finally, Commissioning Level 3, or CXL3, involves startup and system acceptance testing. During this phase, pre-start checks are performed. We verify rotation and safety systems, conduct point-to-point testing, and initiate initial tuning along with setting alarms. Each of these levels acts as an evidence gate, ensuring quality and compliance at every stage before proceeding to the next. This structured approach helps align with the owner project requirements, the basis of design, and measures like power usage effectiveness and water usage effectiveness to optimize overall system performance. In this module, we're focusing on the journey from verifying individual components to demonstrating whole system resilience using time-aligned evidence. We start with functional performance through heat load testing, which includes thorough audits like clause-to-design reviews, drawing-to-field walkdowns, and point-to-point evidence checks to ensure everything meets certification standards. Moving into integrated scenarios, we then apply a representative load and reconcile this with the measured duty, holding the system until it stabilizes to capture accurate data and record uncertainty. Restoration proof involves initiating controlled failures and verifying responses from both automated systems and operators, checking remaining capacity and temperature excursions carefully. To complete the process, we return the system to normal operation step by step, confirming standby availability, addressing all overrides and alarms, and signing off on restoration. This comprehensive approach ensures a robust and resilient system, critical for maintaining operational reliability in data center MVAC environments. Remember, these procedures rely on declared assumptions, with final selections requiring approved project and vendor data. Understanding this framework is essential for adhering to owner project requirements and optimizing efficiency metrics like PUE and WUE. Here we see the architecture for certification-ready evidence in Data Center MVAC systems. The key idea is that code approval, independent certification, and owner acceptance are distinct decisions, but all rely on a common controlled evidence set for transparency and accountability. The evidence pack includes 5 essential stages: basis, design, installed, tested, and operable. Each stage compiles specific documentation like owner requirements, schematics, inspection photos, test results, and operational procedures. The assessment outcome can range from fully conforming to non-conforming, with clearly defined scope, authority, and closure paths for each result. It's important to remember that certification confirms conformity within a defined scheme and timeframe, but it doesn't guarantee future performance or replace ongoing operational discipline. This slide covers the failure mode register, which is crucial for managing risks in Data Center MVAC systems. We start by ranking failures based on their consequence, how easily they're detected, the possibility of automatic response, and the complexity of restoration. For example, a common failure is applying the wrong edition of a document, which can be detected by spotting unapproved deviations. Another critical failure is losing requirements during procurement, often detected by missing test evidence, where the best response is to preserve regulatory evidence to ensure compliance. Then, there are unverified vendor claims that might only become apparent when a calibration expires. Changes in meter boundaries can cause boundary mismatches, requiring a recorded temporary deviation as a response. Evidence stored without an assigned owner can go unnoticed due to uncontrolled software changes. Finally, operations procedures conflicting with design specifications pose serious risks, typically detected when certification actions are overdue, and the immediate response is to rely on safety and approved operating rules. Understanding and addressing these failure modes is vital for maintaining operational integrity and compliance in data centers. This methodical approach ensures we catch issues early and respond effectively, minimizing downtime and safety risks. On this slide, we're focusing on the compliance and evidence discrepancy workflow for Data Center MVAC systems. The key takeaway is that when discrepancies arise, we must first protect the service and ensure safety before making any changes. We start by stabilizing the situation. This means protecting life and IT duties and using approved alternate paths if necessary. Next, we preserve the current state by freezing trends and logs, capturing exactly how things were found. Then, governance comes into play, where we confirm the source, edition, and applicability of the governing requirements. After that, we verify the installed assets, set points, meters, and calibration to ensure everything is measured accurately. Only then do we proceed to correct the issue through an authorized management of change process involving one controlled change. Finally, we prove and close by retesting, restoring the system, and updating the baseline. It's critical to respect the hold point. Stop immediately if there's any uncertainty about safety, authority, or system validity. The entire process is documented with one indexed record, linking the as-found state all the way through to the restored baseline, ensuring full accountability and traceability. Here we have the controlled cutover and migration process, often called the 0-hour operating sequence, which is critical for ensuring a smooth transition in our data center MVAC systems. The process begins at T-7 days with the planning phase, where we secure all necessary approvals, issue bulletins, and define the rollback strategy to manage any risks. Then, at T-1 day, we move into the pre-stage, confirming tools and spares are ready, the team is briefed, and the backup path is proven reliable. At 0 hour, we protect the stable load by freezing operations and activating the alternate path to ensure continuous service. The next step is to isolate and make the change with a single controlled action, verifying isolation throughout. Following this, we verify and monitor system function, alarms, and perform a representative load soak to confirm stability. Finally, we restore and close with the normal lineup, providing evidence of success, while remaining ready to roll back if any limits are breached. The rollback trigger is a vital safety measure. Any safety limit breach, loss of capacity, unstable conditions, or failed proofs must immediately halt the process, restore the last proven state, and escalate the issue. This gate ensures that reliability and safety, are never compromised during such critical operations. On this slide, we're focusing on operational governance and continuous compliance within data center MVAC systems. The key idea here is that the accepted baseline only stays valid through ongoing efforts like monitoring, maintenance, testing, assessment, change control, and evidence retention. We start with monitoring critical metrics such as PUE, WUE, thermal capacity, and alarms to ensure systems perform as expected. Maintenance includes preventive measures like calibrations, firmware updates, and stocking necessary spares. Testing involves checking functionality, failover capabilities, restoration processes, and conducting drills to prepare for contingencies. Assessments are done through operational reviews and security or risk audits to identify potential issues. Change control is vital. It includes managing plans of operation, managing organizational changes, cutovers, rollbacks, and approvals to ensure any modifications are properly executed. Finally, retaining evidence through trends, records, exceptions, and competence documentation supports accountability and traceability. Triggers such as new codes, load changes, alarm trends, or audit findings initiate this governance cycle. The outputs of this process are an updated baseline, closed actions, retested systems, and a current evidence pack. The fundamental control principle here is that no change is complete until the operating state, documents, training, and retained evidence are fully aligned, ensuring ongoing reliability and compliance. In an emergency operating response, the highest priority is always life safety and thermal stabilization. It's crucial to preserve evidence and restore systems deliberately, not hastily. Always start with safety and approved operating rules. This is your foundation. If you notice any unapproved deviations, you must watch closely and escalate the issue through the proper incident authority without delay. Preserving regulatory evidence is equally important. Make sure nothing is missed that could impact compliance. Notify the governance owner immediately if there are issues like expired calibrations. And if you need to make temporary deviations from standard procedures, always record them carefully, watching out for any boundary mismatches and escalating as necessary through approved channels. Remember, terms like OPR, BOD, PUE, and WUE represent key metrics and requirements that guide how these responses are managed to maintain standards and certification. This structured approach ensures we handle emergencies responsibly while meeting regulatory and operational expectations. In this practical lab, we focus on building a clause-to-evidence matrix, which is a critical tool for ensuring compliance and transparency. Our objective is to systematically map out relevant standards and certification requirements to the actual evidence from the Data Center MVAC system. The inputs include adopted code additions like ASHRAE 90.4 to 2025, OSHRI TC 9.9 classes, ISO/AC 30134 KPIs, and specific certification commitments. Using these inputs, we calculate or map the system, declare boundaries, peer check assumptions, and identify any critical uncertainties. The output of this exercise is a marked-up schematic, a detailed calculation sheet, and a risk and evidence checklist. Meeting these pass criteria demonstrates a thorough and verifiable approach to standards and governance in data center operations. In this practical lab, our main objective is to calculate PUE and WUE using declared boundaries. PUE, or power usage effectiveness, is calculated by dividing the total facility energy by the energy consumed by IT equipment. WUE, or water usage effectiveness, is found by dividing the annual site water use by the IT equipment energy. We also look at cooling energy intensity, which is the cooling energy divided by IT energy and compliance coverage, which measures how many requirements are met out of those applicable. To ensure accuracy, we implement controls such as freezing the applicable additions, mapping each clause to a design response, assigning an evidence owner, and verifying installation evidence. Field-proof steps include clause-to-design audits, drawing-to-field walkdowns, point-to-point evidence checks, and meter boundary verifications. This structured approach helps us confidently assess and validate the efficiency and sustainability of the data center's MVAC systems. In this practical lab, we focus on performing a certification readiness gap review for the data center MVAC system. The process involves working through specific scenarios where we identify detection points, appropriate responses, residual risks, and gather evidence. For example, when we detect an unapproved deviation, missing test evidence, expired calibration, or a boundary mismatch, our response should prioritize using safety and approved operating rules, preserving regulatory evidence, notifying the governance owner, and recording any temporary deviations. On the evidence side, we might encounter issues such as applying the wrong addition, losing requirements during procurement, unverified vendor claims, or changes in meter boundaries. Understanding this framework thoroughly helps ensure compliance and prepares the system for successful certification. When we talk about handover evidence and operating readiness, it's crucial to understand that the asset is only ready when all technical, procedural, and competency evidence are complete. Starting with design, we need to have completed the owner project requirements or OPR, the basis of design or BOD, and all calculations, along with approved drawings and PNIDs. Any submittals or deviations must also be documented. Moving on to installation, as-built tags are essential, as well as inspection records and pressure, leak, and cleanliness tests to ensure everything is up to standard. For controls, we focus on the point schedule, sequences and settings, plus backups and access control to maintain system integrity. Testing and operations follow, ensuring the system functions as required. Lastly, competence is key. Everyone involved must be properly trained and qualified. This comprehensive approach ensures a smooth, successful handover and reliable operation of the Data Center MVAC system. In this competency assessment, you're expected to demonstrate real engineering judgment, not just memorize facts. You need to be able to explain key concepts like describing the complete service path and identifying interfaces and failure domains. When it comes to calculations, you'll work with important metrics such as PUE, which is the facility's total energy divided by IT equipment energy, WUE that measures water use relative to IT energy, cooling energy intensity, and compliance coverage to understand how well requirements are met. You should also be capable of diagnosing common issues, such as applying the wrong addition of a standard, losing requirements during procurement, unverified vendor claims, or changes in meter boundaries. Additionally, you must be able to operate systems effectively, prove compliance, and know when to escalate issues. These competencies are essential to managing data center MVAC systems and ensuring they meet standards, governance, and certification requirements successfully. Now that we've covered the core material, let's focus on some essential standards, governance, and certification elements. It's critical to use licensed standards, approved project documents, and current vendor data for the final design and operation of data center MVAC systems. Some key reference families you should be familiar with include ANSI/ASHRAE Standard 90.4 to 2025, which focuses on energy standards for data centers, OSHRI TC 9.9 guidelines on thermal management and liquid cooling, and ISO/IEC standards for power and water usage effectiveness. Also important are EN 50600, TIA 942, and any adopted local codes and project-specific criteria. Let's also review the closing principles to keep in mind. Always track heat from its source all the way to rejection. Distinctly separate design margin from redundancy. Keep local safety and supervisory optimization boundaries explicit, and accept only measured, traceable evidence to validate performance. As a result of this training, you'll be able to develop system schematics, perform calculations, create sequence and alarm matrices, draft test scripts, and maintain thorough evidence checklists. Looking ahead, the next module will dive into air-cooled chiller systems, building on the foundation we've set here. With these standards and principles in mind, you're well prepared to ensure both efficiency and compliance in your designs. As we wrap up Module 02 on standards, governance, and certification, it's crucial to remember that successful data center MVAC system design relies on using licensed standards, approved project documents, and up-to-date vendor data for both final design and operation. Some key reference standards include ANSI/ASHRAE Standard 90.4 to 2025 for energy efficiency, OSHRI TC 9.9 for thermal and liquid cooling guidance, and ISO/IEC standards for power and water usage effectiveness. When finalizing your design, always track heat from its source all the way to rejection. Clearly separate design margins from redundancy, and maintain explicit safety and supervisory boundaries. Importantly, only accept data that is measured and traceable. Your training outputs should include system schematics, calculations, sequence and alarm matrices, test scripts, and evidence checklists to ensure comprehensive documentation. With these principles in mind, you're well prepared to move forward confidently.